So picture this. It's 1789. The French Revolution is kicking off, right? But at the same time, another revolution is happening, a much quieter one, overthrowing an entire field of science. And it wasn't started with a weapon, but with a book, Antoine Lavoisier's Elements of Chemistry. This book was about to give science a completely new language. Let's dig in and see how he did it.
And Lavoisier, he knew exactly what he was doing. He even said it himself. He and his colleagues were getting heat for changing the very language of chemistry, the words and ideas handed down by their own teachers. This was a seriously radical move.
I mean, that's the core of the problem, isn't it? What good is a scientific language if it's describing a world that doesn't actually exist? What are you supposed to do when you realize the very foundations of your science are built on misunderstandings and, well, just plain mystery?
You have to understand, before Lavoisier, chemistry wasn't really a science. It was more like a cookbook full of weird recipes. It was this jumble of confusing, almost mystical names for things, with no real system, no logic connecting them. It was a craft, for sure, but it wasn't a science. Not yet.
I mean, just think about how wild this is. The most basic, fundamental concepts, totally wrong. Water, what we all know is H2O, was considered a single, indivisible element. And fire, nobody had a clue what was really happening when something burned. They had all these theories about mysterious substances being released into the air. So, how did Lavoisier fix this mess? Well, his solution was so simple it was brilliant. He basically argued that chemistry had to stop being about just looking at things and describing them. It needed to become a science of rigorous, hardcore, quantitative measurement. His motto was pretty much, if you can't measure it, you don't really understand it.
And what was his secret weapon in this whole revolution? Something you've probably seen a million times. A simple balance scale. He insisted that absolutely everything, every ingredient going in, every product coming out, had to be weighed with extreme precision. And that one simple demand, well, it changed everything.
And ma'am, the lab he built to do this work, it was absolutely state-of-the-art for its time. He had specialized gear like the gasometer to capture and measure gases, these massive water cisterns, and of course, incredibly accurate scales. This wasn't some mystical alchemist's workshop. This was a modern laboratory. And here's a little quote from him that I just love, because it shows you the scale of his thinking. He built this gigantic water cistern for his experiments, thinking, this is way too big. But he found out pretty quick that for the kind of questions he was asking, even that giant tank was barely big enough. He was always pushing the limits. Okay, so he's got this incredible lab, this new way of thinking. Where does he start? He goes right for one of the biggest, oldest mysteries of them all, fire. What is actually physically happening when something burns? For centuries, the prevailing belief was that when you burn something, it releases this mysterious substance, right? So it's got to get lighter. Lavoisier's response was basically, forget the philosophy, let's just weigh the thing. So simple, so direct.
And this led to one of his most famous, most elegant experiments. He took a very precise amount, 100 grains of iron, and he burned it inside a sealed container. Then he carefully collected all the black, brittle powder that was left over, which they called calx.
And the result? Whoa, it was a complete bombshell. The iron hadn't lost weight. It had gained it. The powder weighed 135 grains. The iron had somehow pulled 35 grains of mass out of thin air. How was that even possible? Right? The weight had to come from somewhere, and since the container was sealed, there was only one place it could have come from, the air inside. And that meant combustion wasn't about releasing some mysterious stuff. It was about the iron combining with something from the air. He called that something vital air. We, of course, call it oxygen. Boom. Mystery solved. So he's just solved the mystery of fire. What do you do for an encore? Well, you take on an idea that's been around for literally thousands of years. The belief that water is a simple, fundamental element. Instead of trying to break water apart, which is what you'd expect, he did something way smarter. He built it from the ground up. In a landmark experiment, he took two different gases, his vital air, oxygen, and another gas we now know as hydrogen, and he combined them. And what did he get? Pure water. And this is where you see his genius for measurement just shine. He didn't just make water, he measured exactly how much of each gas it took. To make 100 parts of water, he calculated you needed 85 parts oxygen and 15 parts hydrogen by weight. The evidence was undeniable. Water was not an element. It was a compound.
So you have these incredible experiments, burning metals, making water from thin air, and they're all pointing to something huge, a single profound truth. Lavoisier was on the verge of discovering not just a new fact, but a fundamental law of nature.
Through just endless, meticulous weighing over and over again, he proved something that would become the cornerstone of all modern chemistry, the law of conservation of mass. In any closed system, the total weight you start with is always exactly equal to the total weight you end with. Nothing is created, nothing is destroyed, it just changes form. He even proved it with something as messy and complex as fermentation, turning grape juice into wine. He weighed the sugar, the water, the yeast. Then he captured and weighed everything that came out, the alcohol, the gas, all the leftover stuff. And look at that. 510 pounds go in, 510 pounds come out. It's perfect, a perfect balance. And this led to probably his most powerful idea of all. He realized that a chemical reaction could be treated just like an algebra problem. The stuff on one side of the equation has to equal the stuff on the other side. He had single-handedly transformed the messy, unpredictable art of chemistry into a science as precise and reliable as math. So when you put it all together, what Lavoisier did was just monumental. He gave chemistry a logical language, he gave it a precise method, and he gave it its first great law, that matter is always conserved. There's a reason we call him the father of modern chemistry. He earned it. And his story kind of leaves us with this incredible, provocative thought. Lavoisier showed that something everyone thought was a basic element, water, was really just a combination of other things. It makes you wonder, what things that we think are fundamental elements today are really just complex equations we haven't figured out how to solve yet?